So somewhere?
No, just type like
Hello everyone, my name's Sam, I'm a community manager at Tungsten. Like I said, I think for a lot of you, you've probably never been to the space, so welcome if you're the first timers. So I just want to take 2 minutes of your time for an awesome talk tonight to tell you a little bit more about what we do. So here at Tungsten, I probably need to get the door as well. Oh, thank you. Here at Tungsten, we are a co-working space, but we are truly dedicated to data science. So we focus on housing data-driven startups as early as they are, or whether they're sort of midway through their sort of early stages. We're not only a community of data science, we have a varied range of startups including fintech, biometrics, video analytics, a bunch of different data-driven companies. So what I like to think is that we're the place to be. We're not only a very cool office, as you can all see, but we've got a great atmosphere and a great community around data science. And one of the ways that we sort of engage our community is through these sort of events tonight. So not only do we have our event space, we have 35 to 40 people, fixed desks, and about 8 different startups here. We also offer our members access to desk space around the world, including San Francisco, Singapore, all the different tech hub cities. So if you haven't already, go check us out online. We're pretty much everywhere. Our social media channels are all here. Please go follow us, especially our Instagram. We're really pushing that hard now. But we also have our blog, and if you're interested in sort of AI, machine learning, data science news, we want to kind of make this the place to go. So we publish fresh stories every week, including videos and podcasts and all sorts of goodies there. We have a weekly newsletter that sort of spins off from the back of that. So if you kind of want a weekly digest of all this data science and machine learning news, you can sign up to our newsletter from our website, and then you'll sort of keep up to date with it. We also have a competition tonight. So if anyone wants to take some great photos of the space, of the talk, all you have to do is hashtag Chat15 on Instagram. I'll scroll through the end of the night, hopefully pick out a good winner. And then you'll be able to win a free day's hot desk in here. So if you're interested in just sort of working out here for a day for free of charge, including our sort of Wi-Fi, all of our facilities here, go take a photo and hashtag it Chat15. That's it from me, but welcome Romeo, and I'm sure you're going to smash it tonight. Thank you guys.
Thanks a lot. The most important feature of this space is, who of you knows the game Ingress? Nobody? One. Okay. So for those who know, there are 3 portals in range here. So while doing the talk, I can hack portals. It's an online game. I'm not addicted, but so let's actually start. I'm actually reusing my presentation, which I gave just in the afternoon at the AI Summit. So you get it for free now. And what I wanted to do, I'm recording all my sessions, but my sessions are very similar, so I have a lot of similar recordings on YouTube. But anyway, if you want to get a recording of this session, just check out my YouTube channel. I have some other data science tutorials there as well. So back again. And yeah, you get that talk for free, and some folks told me it was the best talk at AI Summit, but maybe the reason was because I'm relatively technical, and the AI Summit has had a lot of companies presenting, and they always invite CIOs and CTOs and C star something. So I'm a technician, and I want to know you a bit better in order to tailor make this presentation and workshop for you. So maybe can you just raise your hand? Who of you is a developer? Who of you is using Python? Who of you is using Java? Who of you is using R? Who of you is using Scala? JavaScript? Okay. Who considers himself as a data scientist? Who of you could, you don't have to, don't worry, who could explain artificial neural network here on stage? Okay. Architects? Project managers? So maybe you have programmed 10 years ago and now you are kind of out of that business. Such type of architects? No? Project managers? Anything else? Okay, I think then we are quite set. So today I can tell you a lot of things, and I forgot one thing. Apache Spark, who is using Apache Spark in production? Okay. So who of you would be interested in get some insights how Apache Spark works as part of this? Okay, then I can at least do something on that. Yeah, perfect. Okay, so let's start. So I'm Romeo Kinsler. I'm based out of Switzerland in a worldwide team, and I'm working for the IBM Watson IoT division. It's the first IBM division outside US. It's in Munich, that center. IBM invested $200 million in that, already engaging with 6,000 clients, and you see here a couple of partners, and you see companies like Intel and Cisco and Texas Instruments, I forgot. Yeah, so we are partnering basically with hardware manufacturers. So the IBM strategy on IoT is not to produce hardware, at least until now. Let's say not to produce device hardware. Okay, maybe we have another interesting thing in the pipeline, which I will show you later. It's running artificial neural networks on a specialized chip. That's another story. But why is IBM thinking of doing IoT? So the reason is, you see here, a lot of devices will be connected to the cloud by 2020, and those devices are generating data all the time, and that data needs to be analyzed. So how do we stream those data to the cloud? I would say 90% of people are, at least those who are using the bigger cloud providers, are using MQTT, which is a lightweight telemetry protocol invented by IBM and got a OASIS standard by 2003. And that's all about the IBM Watson IoT platform. So we support 250 devices out of the box, like Raspberry Pis, Edison, Cisco gateways, whatever you can imagine. If your device is not supported, that includes at the moment such a smartphone, you can just send the data using MQTT, and I have a little demo. Oh, I forgot you.
I can make it at the end.
Okay, yeah, I met this guy at AI Summit, and he owns a startup, and he has open positions for data scientists, and I just offered him to do a 1-minute pitch. But
at the end.
Yeah, but tell me, otherwise I'll forget it. Yeah, so we will do this demo later. So that's the device thing. So all is about MQTT. And if you can use MQTT, you can still fall back to HTTP and HTTPS. The IBM Watson IoT platform is a MQTT message broker as a service. And it's an open standard. That means if I'm in the plane, I have to hack something, I'm using Mosquito. It's a little MQTT message broker which runs on my laptop, and then I can immediately switch back to the IBM Watson one. I don't notice any difference. I don't have to authenticate on my local one. That's a big difference sometimes. Then you have some APIs for managing. We will see later how this works from the smartphone, or we will see the result later. We don't dig into the Swagger documentation. And then as the last thing, I'm experiencing some lag between my laptop and the projector, but that's okay. So the last thing is the applications, and then this is where it gets interesting. And we are basically having a strategy that we have some stuff on the cloud, but we can also support any algorithm and solution you have somewhere. This is how to get such data into the cloud. So if you would have used MQTT, native MQTT, then you would have used, let's say, 10 lines of code instead of only 3. But the thing is, you create a connection, you don't see any port or URL or IP address here, because if you're using the IBM client, it's a fault-tolerant system which is deployed to many data centers around the globe, and it just takes care of fault tolerance and failover. This line here is reading a temperature value from the sense set and reformats it as a JSON. So that's a Python dictionary which gets then reformatted as a JSON. And then you see here quality of service equals 2. That means exactly once guaranteed delivery. So once this line completes without error, then you are guaranteed that your message is not getting lost anywhere. If you want to know how to work with that, you can take this course here.
Sorry.
Yeah.
Do you take questions now or after?
You can ask now.
Okay. First question. Do you share the slides?
I can share the slides. I'm currently recording this, so it will end up at YouTube. I will share the link in the Meetup page. Second question.
Well, how IBM shares its platform? Is it like a paid platform or something that we can actually access?
Yeah, that's pretty cool because first of all, we have a 30-day trials like everybody, but I think IBM is the only one at the moment which has a freemium model. So if you sign up for freemium, it's in beta this month, and in next month freemium gets into production. You can use this for free in a limited fashion, and limited means on the platform it's 200 megabytes of data transfer, I think unlimited number of devices, and on the analytics side I think you get a Spark cluster with 2 cores and 5 to 10 GB of storage and some other stuff. So you can actually implement your solution and you get the same SLA as our paying clients. So you can use it in production if you like. And whenever you need to scale up, you have to pay. Okay? That's our idea, that you are getting successful with the platform, you are scaling up, and then you are paying client for us. So if you want to know more about analytics, that's a, let's say, introductory course on Apache Spark in the context of IoT data processing. So I'm teaching you there a bit of NoSQL, a bit of object storage, some Spark internals. I'm using Python, some data preprocessing, Spark SQL, and I end up with principal component analysis. And I'm currently working on the 2 next courses, so I'm taking it from there for the advanced machine learning. And after that is completed, I will create a deep learning AI course. Yeah, so see, that's the last slide and the last exercise. It's the result of a principal component analysis, and you basically plot the data. So that was a high dimensional data set, and I reduced it to 3 dimensions, and here you can basically, for example, imagine a hyperplane or a plane to separate the data. So that's basically where we will start with the next course. So that's all about central nervous system of IoT, and now we'll talk about the brain. And still experiencing some lag. So machine learning on historic data, that's the default. I would say most of you are doing machine learning on historic data. Anyone of you is doing online learning, stream processing? Yeah? Which platform?
Well, Spark Streaming.
Spark Streaming?
Yeah.
Okay. Structured streaming or the D-Stream, the old one?
The old one.
Okay. So I have a working example for the new one. There is a connector called Apache Bahir, which is a MQTT. I don't know if you are in the MQTT context, but for me it's interesting. I have a working example. I can consume those streams in real time, those MQTT streams, and process it with Apache Spark Streaming. So historic machine learning is obvious. You have an algorithm, it sits on top of your data, it runs either single-threaded or in parallel, if you're lucky in parallel, otherwise you get old and wait. So the other thing is online learning, incremental data processing, which is a bit more complicated, and you actually often have to do both. And here are some pros and cons. So of course online learning doesn't need storage. You don't necessarily have to store the data, and you can have an always accurate updated model if that is necessary. But on the other hand, there are not as many algorithms for online data processing or for incremental data processing. They are not designed for doing that, and therefore the software support for incremental data processing is not that good. And also, if you come up with a better idea, a better algorithm, then your data is gone. Yeah, please?
Yeah, I've noticed this thing with the online machine learning that there's not really too many out-of-the-box algorithms available. So the only package that I'm aware of that has some stuff that's called some models and others. Do you have any recommendations for like what's the biggest?
Yeah, so I don't have any open source recommendation now. I'm working on that. I have a closed source recommendation, which is IBM Streams. It has a time series toolkit. But you will see that later. We have an open source tool which is called Node-RED, that is based on Node.js, and we've donated that to the JavaScript Foundation, and I'm currently planning to implement the time series toolkit on top of that. So let's see how I've already implemented moving average and moving z-score, so and I will just start from there. Yeah, and then let's see what the Spark community does in that space. And the last thing is compute power has to be in line with your data rate. It's not that hard since we are in a scalable environment in the cloud, so you can add and remove workers in the Spark cluster, but it has to be considered. So my last demo will run on my laptop, and I have to basically throttle down the data, otherwise my machine explodes. On the other hand, historic data processing have all algorithms available because they start basically using batch processing to implement those algorithms. Therefore, you have an abundance of software, most prominent R and scikit-learn, Apache Spark Machine Learning, and some others. If you come up with a better model, you can just retrain it, or you can do cross-validation, hyperparameter optimization, and you run in batches. So then maybe just the batch takes longer if you don't have enough resources. On the other hand, high storage costs. So I have a use case in Switzerland of a hospital where we store EEG data of patients for 10 years, and they are now in the range of $500,000 of storage cost. And the model can't be always accurate. It's always after the batch has completed, your model has been updated. Who knows what this is? At the AI Summit, I would say 80% of the audience exactly knew it. But that was the first time. Excuse me?
One of those time series jollies.
Yeah, time series, yeah. ARIMA model, good. Very nice. Who of you recognized that as a ARIMA model? Who of you recognized this as a regression model? Yeah, and as a linear model? Yeah, okay, good. Linear, it's because it has only linear components. It's a linear combination, basically. And auto-regression is basically this linear model, and auto-regression means that you actually are using the target variable as predictor. You see here, you are predicting y hat t out of yt minus 1 and so on. And integrated moving average part comes from these error terms, but I don't want to dig too much into detail. You are trying to predict a nonlinear function out of a linear model, which works somehow. I don't know, I'm not an expert on that, but I was directly digging into deep learning for that. So you see here the Google trend charts for Spark and deep learning. Definitely they are peaking. I think Spark already peaked. It went down, but they are kind of correlating, I would say. And there are frameworks which are able to run on Spark. Currently there are 3. It's deep learning for J and system ML and TensorFlow using TensorSpark, which I haven't tried, but I will do soon. So there are some non-machine learners in here, so just the others please stick with me for 5 minutes. So that's a hypothetical table of an Industry 4.0 predictive maintenance use case, and you have to predict the outcome, faulty or healthy, based on that data set. So how could you implement that manually?
We allow weighted sum.
Excuse me?
Thresholding a weighted sum. Weighted sum and then thresholding.
More easy?
Part number greater than 102 predict 0.
Yeah, vibration greater than something, no? That's more easy. The other 2 columns you can basically forget. It's an artificial example, just to illustrate. That would be a so-called white box model because you understand the physical system in place and you implement the rules. Okay, very easy, but that I think illustrates it properly. What about that one? How is that model called? Yeah. So can you tell me the parameters A, B, C, and D in order to train this model for those data? Yeah. So what is A?
Bias.
What number?
In this case, it's 1.
1 is good. Yeah. Then B.
B is 0, C is 0.
Good. D.
1500 over 2.
1500 over 2. I would have to check that. My solution is -1 over 3412.
Oh yeah, it's
Which-
going to be minus.
Yeah. And that basically doesn't give me a binary classifier. So what do I need to do to turn? Excuse me?
Triple.
Yes, I could find a threshold maybe, but in order to be a bit more clear between 0 and 1,
Rounding.
round it. Other ideas? Heard about logistic regression? Sigmoid? Have you heard about sigmoid? So sigmoid basically just squashes any range between minus infinity and plus infinity to a range between 0 and 1. And then you're right, you could put this threshold somewhere near 0.5. In order to optimize, just for those who are interested, in order to optimize for that threshold, you can use a ROC curve and you can maximize the area under curve in order to get the optimal value for the threshold. And also you can tune the false positive and false negative rate with that, but that's beyond the scope of this. But what I want to tell you is that a single neuron can be expressed as a logistic regression model. Okay? Because all what you do in a single neuron in an artificial neural network is you take the input, those are the x1 to xn, and then you have weights w1 to wn, and then you have a transfer function, which is sum. I have never seen anything else than sum, but it's specified here as a pluggable function. And until here you have linear regression, and then there is a so-called activation function, which can be sigmoid, but also there are others like TAN, H, rectifier, ReLU, or whatever. You can Google for those. Oh, actually, you cannot Google, you can Ecosia. There's a new search engine, ecosea.com. It's a Berlin startup, and they are donating 80% of their ad revenue to plant trees. Yeah, so that's the single neuron, inspired by a biological neuron. So that's one neuron in your brain. So you have inputs. The dendrites are the inputs of the upstream neurons, and then there is one connection, the axon, and that goes to many other neurons. And the connection between neurons in your brain are synapses, and those are biochemical connections, and those are modulated. So whenever signals are passing through the synapses, they are getting stronger, that connections, and also the amount how they get stronger is also modulated. That's a very, since we have a bit of time, I tell you that biochemical process. There's a neurotransmitter called dopamine, which gets released if you are happy with something you have done. And the idea behind this, you want to learn that. So if you have achieved something, you are getting happy, and that triggers the synapses to form better. But there is a big catch. Dopamine gets also produced, so it makes you basically happy, plus it makes you learn, and it gets released if you drink alcohol, if you smoke cigarettes, if you're taking any drugs, if you are addictively using either this mobile app game I'm doing, or on Facebook, or whatever you do, then dopamine gets released, and the bad things you then learn to love the addicted stuff. No, that's the problem. So whenever you want to learn, just don't abuse drugs and just learn. And whenever you learn, really, then you get this good feeling, and that's dopamine, and that triggers the synapses to grow faster. Okay. And by the way, if you are stressed, that process is completely stopped. So if you are stressed, that means tiger is behind you. So you won't imagine how the world can be, how your head can be improved. You just want to find a tree. Okay. So all that dopamine gets stopped. So you get sad when you are stressed, and your creativity is gone because you don't have to be creative. You just have to run for the next tree. Okay. That's interesting, and that's something artificial neural network, as of now, doesn't do. Training artificial neural networks works differently, but that's beyond of the scope. So I'm only telling you how the forward path works and how those weights are affecting the actual data processing. And that's now an example of a feed-forward network with a single hidden layer. And the single hidden layer is there for a reason. The hidden layers are learning data or feature transformations. And such a neuron can be implemented really easy. You don't have to do that because there exists an abundance of neural network libraries in any programming language. But the idea behind that is for a single neuron, you take the dot product or the vector-vector multiplication of the weights and the input data, then you get basically the same as linear regression. And that's basically the key thing you have to understand if you want to understand the literature. So if you don't know how that works, please Google or Ecosia for vector-vector multiplication and for vector matrix multiplication, because if you once understood how this works, then you won't get stress hormones when you read math, only dopamine, because then everything is easy. Okay, if you are looking at some slides and you don't understand nothing, most likely in that area, it's because you don't understand vector-vector and vector matrix multiplication. Because it turns out that a linear regression model is nothing else than a vector-vector multiplication. And if you want to calculate multiple of those, then you use a vector matrix multiplication. See, the code doesn't change, but it's a vector matrix multiplication. You have no clue what's going on if you don't know how that works. But what you're actually doing is you are calculating multiple linear regression models in just one command. And then you put all that stuff into sigmoid. And also it turns out that Python and R and those mathematical languages are capable of using the same signature for a scalar or for a matrix or for a vector. So it doesn't change at all, but the computation which runs behind that code is completely different. So please have a look at vector-vector and vector matrix multiplication and some linear algebra, and then nothing can scare you anymore. Here you see, if you add a second layer, it's nothing else than just putting the result of the first layer into the second one. And that's called stacking. You are basically stacking multiple logistic regression models, and then you get deep feed-forward neural networks, like this one. And again, here the idea is every intermediate hidden layer will learn another feature representation, because those neurons are not connected or not doing jumps between the layers. So that means always the input for the subsequent layer is the output of the previous layer, and in every intermediate layer new features are learned, which is very, very easy to see using the convolutional networks example, which is mostly used for image recognition. Here you see the first layer, what he's actually seeing, and you see it's inspired by our brain. Our brain works the same. You only see rectangles and circles and lines. So if you see my face, your first layer in your visionary system only sees lines and circles, and the more you go up, so that's maybe in the middle. Of course, these are deep, very deep networks, but if you sample the middle layer, you get some eyes and noses and mouth. And at the end, you get faces, cars, elephants, and chairs. But you see here, it's very, very similar at the first layer. And that's actually because those are called filters. And that's actually the same like the computer vision guys are doing. So if computer vision guys are doing so-called feature engineering or feature extraction, they have such filters, and it's interesting to see that those filters are learned, okay? And that's the key thing on deep learning, the data transformation in order to make the algorithm performing better are learned using the neural network. You can do some art, and it's not my idea, it's from somebody else. It's called neural style, so you can search for neural style. It's an implementation in a framework called Torch, implemented in a programming language called Lua, and that's the example of the author. It's the Golden Gate Bridge and applied to various styles. And that idea, and I think even the author now works for a Swiss-based startup which is running on the IBM cloud and is using the GPU clusters we have in order to have this as a B2C model. You get it for free if you wait for 1 day, or you pay $2 if you want it immediately. So you're basically skipping the queue, and you get a poster for $25 also. So if you're interested in that, check deepart.io. And key takeaway from feed-forward neural networks is that they are capable of learning any mathematical function. Capable means they can represent any mathematical function, but it's not guaranteed that you are able to train this function you are searching for. That depends on various parameters and on the quality and of the amount of data. But at least the tool is powerful. But I'm working in what's an IoT, so I'm working on time series data, structured time series data. So I want to also take the time domain into account. Therefore, another class of neural networks exists. Those are called recurrent, and they have loops. And loops actually allow the neural network to remember state. And for example, if you have 100 layers, you can remember 100 time points. That means you are not capable of remembering or recognizing temporal patterns which are very distant. Therefore, we have another neural network which is called LSTM, long short-term memory network, and that has a memory cell in the neuron, and you have 3 additional signals. One is input, forget, and output. So input controls whenever the neuron has to remember something, forget controls when it has to forget it, and output controls whenever it should output its internal memory to the next neuron. So that's more math on that, and I will stop here, but that's an example of a LSTM reading text as an input stream and being trained on that text, and afterwards it can be turned into a so-called generative model, and it can create this text without knowing anything about English or grammar or words, even words or sentences. It's okay, it's like 2nd grade school. And also LaTeX code is, you can train it with LaTeX code, you can train it with a Linux C kernel. It's all generated by the neural network. Music, but it's really bad music, so I don't play it. But it outperforms state-of-the-art time series algorithms. And the thing is, there are not too many publications on that. So I've only found 3 or 4, and I have actually replicated one of those, and it really works. So I'm wondering why there are not enough or not so many publications on that. Maybe everybody is now jumping on that image recognition and natural language processing topics using deep learning, and that's maybe a bit abandoned. So I took over, and I really will implement more stuff in that space. So that's from that publication. You see on the top left a time series of an ECG sensor, and it's labeled, so you have blue for anomaly and green for normal, but that information is not given to the neural network. And you see clearly that it recognizes that anomaly with a nearly 100% accuracy, so it completely drops to 0 here. the probability. So the probability value tells how likely have I seen this data before. And it's 0 here, again here. So that top left example, I even could spot it, but on the top right hand side it's a bit more complicated. But it's still able to spot it, again with a probability of 0. And then what happens is it goes up, even if it's faulty. So any ideas why this is happening?
Sorry, what is the example at the top right? Is that ECG as well?
That's energy demand. That doesn't matter.
Okay.
The question is, why is the spike only at the first occurrence of the anomaly and not at the second and third? Excuse me?
It's happened before.
Well, it updates itself.
Yeah, but you're cheating. You have attended my talk. Yeah, so it basically learns. So the learning is always enabled. You can basically turn learning on and off, but it's always enabled. So it learns also the anomaly behavior, and that's kind of a proof that it works now. So what you need to do is two things. You can run a downstream algorithm on to detect those spikes. And also what you have to think of whenever you want to reset or turn off learning. That's another unsolved problem, even in my projects.
Sorry, what was the, first of all, was it unsupervised?
It's unsupervised, yeah.
What architecture did you use?
It's I didn't use that. That's another topic from somebody else. A publication. They are using a LSTM, a long short-term memory network, which is capable of remembering past state, and therefore it can remember what it has seen before, and therefore creating this anomaly. I will show you later how this works, because I have re-implemented exactly that publication using deep learning for J, and I even can share that code. So that's time series forecasting, and here you see kernelized regression. I don't know what kernelized regression is. I don't know what a kernel is, so I'm thinking they are using some nonlinear kernel applied to linear regression to get some nonlinearity, so it should perform better than ARIMA. And you see it's 8.3% root mean squared error. And the next thing is the frequency neural network. And the frequency neural network they are using is fast Fourier transformation. Who doesn't know what fast Fourier transformation does?
Who doesn't know?
Who doesn't, yeah?
Yeah, I don't
Okay,
know.
so it transforms from the time to the frequency domain. So basically it returns the spectrum, all the frequencies which are present in your time series. So you will see that later, you will understand it later. So that is basically using FFT as a so-called feature engineering step, and then feeds that into a feed-forward neural network. You get 6.7% RMSE. Next thing, that's the interesting jump in my opinion, or one of the interesting jumps. You remove the FFT, the manual feature engineering, and you add some additional layers to the neural network, and that outperforms the FFT preprocessing because you have 5.9% RMSE. That means you are learning something better than FFT using the neural network, which is great, no? And the last thing is the LSTM, which then basically has 2.8% error. So those two papers inspired me in order to try it myself. And then I discovered that LSTM is Turing complete. Who doesn't know what Turing complete is? The Turing complete comes from theoretical computer science and basically means every system which is Turing complete is, let's say in layman's terms, capable of doing what my laptop is doing. So whatever runs on a modern microprocessor, a microprocessor is Turing complete. So in other words, that means the LSTM can learn everything what you can implement in any programming language. Again, with the constraint that representable doesn't mean trainable. You need to have the good data and a lot of data to achieve that, and a lot of compute power, because they are not so easy to run. They need a lot of resources because you have so many parameters to learn and to process, in contrast to traditional machine learning like regression, support vector machines, or boosted trees or whatever. So you have to check whether it is worth for the additional computational cost. Here's an example of one cluster, 16,000 cores, 1,000 nodes. But there's hope you get the same processing power 7 years later in one NVIDIA Titan M60 GPU card. And I think now we are on P100, so they are even faster. And there's even more hope, because you can imagine how much power this one consumes. I think that particular one consumes 2000 watts, and that one consumes 4 watts, and that's the same computing power than that and that. And that's the IBM True North. It's an ASIC. Have you heard about the term ASIC? Application Specific Integrated Circuit. The most prominent ASICs are the Bitcoin miners, for those who want to dig into that. But that means the algorithm is kind of hard coded into the chip. You cannot change it. Okay? And in that chip, you can only run feed-forward neural networks at the moment. But they are fast and energy efficient, even there is no clock. So the signals are propagating. They are kind of managed to get the same length of all the connections somehow, and then they don't need a clock. The signals just propagate at the speed of whatever they are having on the connections in the processor. And currently IBM builds a 4000 chip cluster with 4 billion neurons and 1 trillion synapses. Of course, the synapse in this case is only a weight, so it's only a multiplication. In contrast, the human brain with 100 billion neurons and 100 trillion synapses has biochemical synapses, which are far more complicated to simulate. So to simulate a biological neuron, you need the compute power of this laptop.
Is the chip just evaluating feed forward, or is it training as well?
It's, I would say, only scoring, not training. So the idea is to put a model on it and, for example, put it into a smartphone or in a car. And the algorithms they have already implemented are for moving object detection. So they can track and detect pedestrians, bicycles, lorries, and cars, and also then calculate potential collisions out of those. So that's an interesting use case. So now, shall we do a 5-minute break? Yes, no? No? Okay. Let me check. So you wanted to hear something about Spark. So let me do a little Spark introduction, and then we can basically run the demo, which runs on top of Spark, and also use the platform to capture data. And the last demo actually shows you the complete pipeline from a physical model, which generates simulated data through the platform, MQTT, and then gets the data and feeds it into the neural network. So I have to say, I wasn't prepared to give the Spark tutorial, but not a problem. So I'm a lecturer, so I will just take this slides from my lectures. That's a PDF. Yeah, that's okay. Let's take that PDF. No worries. So sorry for those who already know Spark. Maybe it's a bit boring. Maybe if you're lucky you don't know Spark SQL, then you at least get something out of that. So if you are using scikit-learn in Python or R, then you're running a single thread. If you're lucky, you are running in multiple threads, but still a single process. And it's hard to occupy a cluster, and often it's hard to occupy all the cores on your laptop. On my laptop, I have 4 physical cores and 8 virtual cores. And if I'm running a standard support vector machine in R, it runs on 1 single core. Okay. So the idea of Spark is to parallelize this. So you basically still have a single process, which is then turned into the so-called driver. Here it's JVM because it's all on Java virtual machine. It's implemented in Scala, but it runs on a Java virtual machine. And then you have the executor, which runs your algorithm, but then you have many executors, and they can occupy all the cores on your node. So there are 64 cores and 128 virtual cores, servers which you can put into your cluster in the cloud. Then you see you have a lot of power on the cluster, and if that is not enough, just use multiple. That's the idea. And then about storage, 2 options. you can attach storage to a central place, and that's the architecture most of people are using nowadays, because the storage just got so fast, and there are also technologies called switching fabrics. So you have, for example, a 2 times 10 gigabit LAN and a switching fabric which guarantees you point-to-point speed of 20 gigabits then between the storage and each node, and that's more than sufficient for most of the cases. If not, you have still the old-fashioned HDFS, Hadoop Distributed File System, where you partition your files. Of course, that is done in the background, and then you have one virtual file, and the idea behind that is that since you are partitioning your files and put it to multiple hard drives, and the hard drives are directly attached to the server machine, then you get the aggregated bandwidth between the hard drive and the CPU on the complete cluster. Okay, if you have 10 gigabit between the hard drive and the CPU, and you have 10 cluster nodes, you get 100 gigabit aggregated bandwidth. That's necessary if you want to have fast I/O, so there's an option for that. Then, who of you is Java programmer? Okay, there's the notion of collections. Have you heard about collections? This just lists of data. In Python, those are called arrays, I would say. And it's always limited to your main memory. In the Java space, it's the heap size. I think in other environments as well. So you cannot create lists or arrays bigger than your main memory. And the RDD is a central data storage object in Apache Spark, which automatically gets distributed on the cluster, and it resides in the aggregated main memory. So if you have 10 nodes with 100 GB of main memory, then you have 1 terabyte of distributed main memory, and the object is transparently distributed among those. And even better, if you have 2 terabytes and you have only 1 terabyte of aggregated main memory, data gets automatically spilled to disk. It gets slower, but it still works. So no out-of-memory errors. You get out-of-memory errors at other places in Spark, but not for that problem. And they are lazy. That means until you are not executing operations on this object, nothing happens. Yeah. Yeah, and that's the cool thing. All Spark programs are parallel. You can implement it on one core and put it to a 1,000 core cluster. The same code runs on both. And also RDD can have 1 KB or 1 petabyte. From the code perspective, you won't notice a difference. And data and task distribution is transparent for you. Okay, so that's all for the introduction to Spark. Then I will do that fast, but it's basically, I will do it fast because it's, since version 1.6, everybody's using the SQL API anyway of Spark. But how this actually works is using functional programming. Anyone familiar with functional programming? Which language? Python? Spark, okay. The idea is it's not to be confused with procedural programming. So functional programming actually means the function is a first-class citizen. You can call a function, and as a result, you can get back a function, or you can call a function as a parameter you pass in a function. And Scala is the most recent representative, and also Python, R, and Java have some rudimentary support for functional programming. So the kings and queens are Haskell and Scala and those. And the idea is basically the following. You have some sort of a means of creating such a function. Either you get it back from another function, or you create it inline, or whatever. So that's your function. In this case, the function does nothing else than everything what you put to the function, it will be incremented by 1. A very simple function. And then you have a list of data. That's your 1 petabyte of data. And then you apply the function to the data. And as a result of doing this, you get the result of the function executed. So every item is just incremented by 1. And that's the way how to, yeah?
Do you explain this in your course as well online?
Those are actually taken from my course, stolen from my course, yeah.
Your online course?
Yes, the Coursera course one. So how can I parallelize things now? I take the same data set, I divide it into multiple parts, and then I send this function to all my cluster members and have this function applied to my data partitions. And now I get an easy three-way parallelization of my problem. And I can decide the amount of parallelization without changing code. That's the idea. Okay? Because those three functions are now working parallel on a subset of the data and still will produce the same result. That's the most easy example. That's called map in Hadoop and in Spark, and apply in R, and in Python I think it's map, and in Haskell I think it's apply, I don't remember. Yeah, so that's about how parallelization works basically in Spark. But now comes the most interesting part, because you actually don't care. It's interesting to know, but there is Apache Spark SQL, and that has three advantages. First, it's SQL. It's ANSI 2003 compliant. So, okay, we can discuss that later. Okay, it has four advantages because you can mix the RDD API with the SQL API anytime. So it's ANSI 2003 besides modifying operators, so it's a select operators are supported. Relatively complex SQLs are already run against that without complaining. So you have still RDD. Like I said, you can always get back the RDD, but you have a wrapper called data frame for R and Python and Scala and Java, and either a relational API or a SQL interface. So you either can say select star from, or you say data frame dot select or dot group by. And the result will be the same, and you can also mix those. I will show you later why and how. And another thing is there's called something called a data set instead of a data frame, and that's strongly typed, and it runs only in Scala and Java therefore. But it's even faster for a couple of reasons, which I will tell you later. So RDDs are schemaless, and data frames have a schema which is either lazy and inferred. If you are reading a JSON file or a CSV file, it tries to predict the schema, or you can explicitly define it before you read the data. So two important components are coming with that. One is the catalyst, which is an optimizer. Optimizers are known from relational databases, but now you have also an optimizer for Apache Spark, and it's a cost-based optimizer, so it takes the amount of data into account in order to generate an optimal execution plan. And the execution plan actually uses RDDs under the hood. So you don't have to use the functional API. You write SQL and you are using the relational API, and then you get an optimal, or let's say a less suboptimal execution than you would have done using RDDs. And then another thing is the project Tungsten, so which has a couple of tools which it uses. So for example, the Java virtual machine has something called a garbage collector, which is responsible for memory management, and that's not the best one if you know how your data looks like on the heap. And Apache Spark knows this because the data frames are typed, so all the sizes of the different columns are known before, so it can do its memory management on its own. So they kicked out the garbage collector and also saved a lot of main memory, because in Java a string with 4 bytes uses 48 bytes on the JVM, but using Tungsten it uses 4 bytes. And there are some more advanced things, I will skip those, but it's actually making your code nearly as fast as somebody would have written it by hand for that particular task. Okay? So for example, if you are executing a SQL statement, then an execution plan is generated. That's the so-called Volcano iterator model, and that involves a lot of inter-process communication and overhead. But if you are using that Tungsten system in Spark, tailor-made Java bytecode is generated matching your SQL statement and matching your data types. And that even works better with data sets than data frames, but only in Scala and Java. Okay, so enough of Spark. Let's do our everybody wakes up demo. And we are using Spark SQL in order to analyze. So I will just tell you what the demo is all about. It is a web application or mobile web application. You can open it on your smartphone. It reads the accelerometer sensors from your smartphone and sends it to the IBM Watson IoT platform using JavaScript MQTT library. And it also registers. Let me go back to this one. I told you right at the beginning, there are APIs in the platform, and since all the devices are security enabled, it generates username and password for you, which you have to provide. And then it already starts connecting to the cloud using MQTT and produces data at the sample rate of 10 times per second. It samples the accelerometer sensors and sends the data to the cloud. And basically I can pick that data up and run a little SQL statement on top of it. That's the demo. Okay. So of course you're not obliged to do so, but I would be happy if you participate. So that's the Watson IoT platform. That's the demo I ran at the AI Summit before. So I will just delete all those devices. And hopefully you are creating new ones. So please open this URL. You are asked for a username and a password, and you have to use a device with the accelerometer. I think an iPad might work. As username, just choose a 8 lowercase character string and just use the same as password. And remember your username, because later we will do the analysis. You can also type it in ibm.bic/boom-boom-shake-shake, or you just use the QR code.
Does it matter what is the username? Anything?
It doesn't matter, but I recommend for 8 lowercase characters. Maybe it is fixed, but there was a defect that it didn't accept uppercase or numbers. I think it's fixed, but just to be safe, for 8 lowercase characters as username, the same as password, or anything else as password. Or maybe the password should be 8 characters lowercase without numbers or something. There was a bug, but.
Sorry, what happens after we do this?
You have signed the IBM Cloud contract, $100 per month, and I get the promotion. No, it's actually a mobile website, and using JavaScript, it reads the accelerometer sensors in your device and sends those 10 times per second using MQTT to the IBM Watson IoT platform, which is an MQTT message broker. So that's the first stage, and then we are streaming that data into a NoSQL database. I will show you how to do that in 20 seconds. And then we will grab the data using Spark SQL and do a little analysis.
So what is this actually doing? Because it's going up published messages every 2 seconds.
Yeah, you are sending data, you are netty. So I tell you what it is doing. So you see here, that's the Watson IoT platform. I click on refresh. So you are here.
Yeah, that's me.
And I click on you. I click on your representation in the Watson IoT platform, not on you. And then it should show. So those are events. So you are sending 10 times per second the actual acceleration of your device. And that should be around 0. I have a performance problem with my browser for whatever reason. Yeah, let's skip that. So if I would have clicked on that, it will just show you the data, but I can show you later how this looks like. So let's do another refresh. So 10 of you are now participating and sending data, and I will just show you how this looks like. So this is the data streaming in. We'll just deactivate this because it takes a lot of resources on my browser because it's a JavaScript thing.
What kind of data?
So I will tell you.
Oh.
So no problem. So the smart. No worries. No phone numbers. The only your Twitter account. No.
It's okay, you guys can follow.
So the web page you have opened,
Yep.
it reads via JavaScript the accelerometer sensors in your smartphone, and then sends those data 10 times per second using MQTT to the IBM Cloud Platform. And here I'm connecting to the IBM Cloud Platform and actually reading all the data from all of you. Okay, this tool here is called Node-RED. As you can see here, it's a JavaScript-based data flow editor. Again, I mentioned it before. It's open sourced. It's donated to the JavaScript Foundation. It runs on top of Node.js. It is deployable to the IBM Cloud in one click or one or two. It runs on all the other clouds. We have checked that. It runs on a Raspberry Pi, on an Intel Edison, on my laptop, anywhere where Node.js runs. It consumes only 64 megabytes of main memory at the moment. So what I'm doing here is I'm getting the data from that MQTT message queue. It's 10 times per second times 10 participants at the moment. So it's 100 hertz. It's a data stream of 100 hertz, 100 messages per second. See, still. And now what I will do is I will stream that data into a NoSQL database, Apache CouchDB. It's only that connection necessary. It's IBM Cloud Platform as a service, so all the tools and databases and whatever you can imagine are out of the box. And now you are in charge of shaking your device. Whenever I click on that deploy button, it starts recording data into the NoSQL database. But remember, the challenge is to create a lot of energy, and you have to invent a shaking pattern in all 3 dimensions. This doesn't work, no? Okay. Are you ready? Okay. 1, 2, 3, and boom, boom. Shake, shake. 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 Oh, broken. No. Boom, boom. Shake, shake. And stop. You can continue shaking, but now the data is not recorded anymore because I've removed the connection to the NoSQL database, redeployed. So let's see if the data arrived. So that's now a UI which comes from IBM. If you don't want to use that, you can use any Apache CouchDB tooling because we provide you with the endpoint, the API endpoint. You see here, 577 messages are in that database. It gets automatically created. It's a lazy, so no need for any create table blah 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 things anymore. And so that's one example of one participant who is Centellas, you. So at that timestamp you have shaked the device not too hard. But it's sampling, maybe you just have been at the top or lower amplitude, so no worries, you still have chances to win. So that's now in a data store. Apache Spark supports various data stores. That's a NoSQL data store. It supports streaming, it supports relational databases, and it supports files, object stores, HDFS, and you can mix and match because all what you get is some virtual SQL or relational representation out of it, and you can even join those data stores. You can join a file against the relational database and then further join it against the NoSQL database. Totally great. And you have the Tungsten optimizer in place, which even is capable of, for example, pushing down a filter to the NoSQL database. So if you have a where clause in your SQL statement and the data source, or how is it called? It's called that's data source. Yeah, it's called data source. There's a data source interface in Apache Spark, and you can implement traits. Those are the interfaces in Scala. So they are calling interfaces traits. And there's one trait, for example, for the filtering. And if the data source supports filtering, like a relational database, it supports filtering based on a where clause, or MongoDB or CouchDB are supporting filtering. That filtering is done by the database, and only those data points which are matching the criteria are sent back to Apache Spark at all. So it's really, really, really cool thing. And now let's actually do the analysis. Who of you I actually wanted to do shit, I messed it up because I hit the back button, and I hit the back button when the notebook was in read-only mode, so I have to reopen it. And somehow my browser is slow because maybe of the remote presenter, I don't know. So I go here to this pencil. Took me half a week to find that out because they are basically improving that tool once in a while, and then I actually forgot to mention what you are seeing here. It's called the IBM Data Science Experience, which is, with some other components, Jupyter Notebook, which is the UI you are seeing here, and an Apache Spark service and some other stuff. Okay, it has also it's called Watson Machine Learning, where you can use Apache Spark machine learning to create pipelines and expose those as a REST API and other cool stuff. But here we will only use the notebook, the Cloudent connector, which is connecting to CouchDB, which we call this database AI Summit Meetup, because it's the meetup after my AI Summit. And now we create a select query. Who of you is capable of creating a SQL statement for me? Who is brave enough? We can do it. So that's a good question. The query should calculate the energy created for each participant in that time window. And the energy you create, you can approximate by approximating the integral of the function of the time series. That's basically the surface under the curve you are plotting. And you have 3 dimensions, so you have to sum that up.
So we can select ID.
Okay, select is good, select ID.
Comma.
Yeah.
Sum of energy.
Sum of energy.
From the table I don't understand.
Yeah, from, it's called, still I have to update this once, but I forget. Yeah.
Group by
Yeah.
the ID.
Okay. You think it will run?
I guess.
Yeah, I guess not, because it will tell you there is no energy column present.
So energy is just the sum of AX, AY, AZ.
No.
Comments.
Yeah. No. Sorry. Sum of AX plus sum of AY.
I don't need the element wise, so not good overall. I have to put it from
I'm showing this because I have the running statement in my clipboard. Not bad, not bad. Nearly there. It doesn't run because, or will it run? Yeah, it will run, but it's not generating the result which you see here. So it should create energy. It should sort on energy.
Don't want abs as well, because when you
Yep,
negative
correct.
you don't want to subtract it.
So where do I
Abs will
put?
be
Okay, what else? Take your time, I will just hack another Ingress portal in the meanwhile.
I mean, what else do you want to do?
I want to have it sorted by energy, descending.
Oh, yeah. Right. Order by.
Order by. You have to name the column.
Order by the
Type.
Okay, I guess that runs.
typo.
Okay, I guess it doesn't run. Where's my typo?
Order group by ID order.
Order. Order means or in German. By the way, you can learn a lot of about how your brain works by making mistakes like those, because somewhere in my brain I was thinking about the term or, and that somehow got translated to order in German, and while typing it just got spilled down to the keyboard.
You learned that too.
Excuse
I
me?
do that a lot with myself. I never learn anything.
Okay, actually you learn that certain areas in your brain, because you can do the same stuff under a fMRT scanner, and then you learn that certain areas of your brain are doing different things, which actually is interesting. But yeah, you can correlate things which are going on in your brain with certain areas, which might be helpful.
So it's
But
the cat that records everything.
yeah, the cap is not that useful because those are EEG sensors, but the fMRT, functional magnetic resonance tomography, I think, whatever, that can basically tell you which region of the brain is consuming a certain amount of energy by the amount of oxygen which is flowing through, and it's on a time scale accurate to, I think, 1 second or so. So yeah, whatever. Yeah, so let's see if that. Of course, I have to first run this one, so that initializes. So you see here, it is transferred into Apache Spark job, which then runs in parallel on the cluster. And now I can run this statement. Let's see what happens. So it's done. Oh, wow! Cool.
That's good.
I wasn't looking at your shaking pattern. How did you shake?
In run like that.
Okay.
And I'm not even on the list. I shook so hard, eh?
So who?
Yes.
I think it should
Jim's
be
panel.
the square root of the sum of the squares. Because you don't want to. If you go on one axis,
Yeah.
you could just do that in diagonal, and you really want like the highest in any axis.
I'm too tired to understand it at the moment. You have to explain that to me later, and I'm happy to update my SQL script accordingly and share that with you. So instead of getting some sleep, let's do the deep learning demonstration. Or do you have any questions until now?
Yeah. So what did this do? Did it? Because it's not a very big data set, so I guess it doesn't need to partition it, or but all of this task
Ah,
looks like
yeah.
it's partitioned it, or
Actually, in this case, if you are reading data from no SQL database, in that case the Apache CouchDB, it will benefit from all the traits which are implemented on the data source.
yeah.
And I think on that one you have the filter trait at least, so it doesn't benefit from that because you have no filter in the SQL criteria. And I doubt that the group by can be pushed to the database. But you can also imagine that data is now running, lying in a object store like OpenStack Swift, which we support because IBM is open. So we have open source, open standard object store, and you are basically storing it as a Parquet file. And then what happens is that if you, for example, select ID AX, AY, and AC, then you can benefit from the Parquet file because Parquet file is a column store. So it won't read the fractions of the file which are containing the columns you don't need. Yeah, so that depends on your data source what you are benefiting. But In the worst case, what happens is that all the data is sucked into the Spark cluster, and then it consumes the main memory and disk, this billable disk, in order to process it. But in case of the Parquet file in object store, the data will remain in the object store, and only those fractions you need are pulled.
Get a query plan out of it to see what it
You
actually
can, I think, yeah, you can, and I think it's called describe. Let me check. No, I still get a data frame back. Let me just search for it.
It's going to show that the PDP thing.
Excuse me?
Will it show the PDP that you mentioned earlier?
The PDP?
Yeah, like the physical plan.
Ah, yeah. The PEP, physical execution plan, yeah. It shows that explain.
You can also find in Spark UI, just for
Excuse me?
if you go on a Spark UI, you
Yeah.
can actually see for the job, you can see the
Ah, okay. But I thought it was. Did I run? Ah, explain, not describe. Describe is yeah, exactly. It's explain. So let's see. Ah, yeah, that's the physical plan. So let's see what happens. There is a hash aggregate, and you see here, those are the functions. And hash aggregate means basically it hashes the group by column, the ID, and creates hash buckets, I guess as RDDs internally, and then on top of those RDDs it will use functional programming and send that sum function to the RDD. The RDD is a structured RDD, so it basically can address the AX, AY, and AC columns. Then there is exchange hash partitioning. That actually is has something to do with parallelization. That actually means it tries to put those groups on different cluster nodes. Of course, it doesn't make sense for that size, but you see it's possible. Then another hash aggregate partition. Okay, what happens then is it will sum on the partitions, and the partitions here, the exchange hash partition basically also partitions data which are containing the same key, and then the partial sum will then be summed up on the partitions which are containing the same key, somehow like that, I would say. And at the bottom you have scan, cloudend, read, write relation, and that's basically pulling the data from cloudend. And I'm not seeing any trait here, so it's just pulling all the data. Let's do just one thing to see if that is already implemented. Excuse me?
I just wondered why it had those OG fields, so to speak.
Yeah, they are also pulled, so it even doesn't filter. But I want to see where ID equals. Let's take any of those. Let's take the winner, NADDY, NADZ. NADDY, NADZ. So I hope this works. So we are filtering now, and here you see pushed filters. So that's now a filter which has been pushed down to Cloudend or CouchDB, and it only returns those tuples. Yeah, that's the idea how it works. And depending on the data source, there are more or less of those push down filters available. Yeah?
apart from the coordinates and the Twitter account, what other data you got it from the mobile phone?
No, that was fun. I'm not getting your Twitter account. So actually that particular application only reads accelerometer values for each dimension and the gyroscope, which is the angle of your phone. There's another app which is called Record Data from the Technical University of Munich. So we are partnering with those, and they are now integrating that to the platform as well. But you can check this out. It already works, and it can store all the data to a file, and it records like 20 data points of all the available sensors of your smartphone, even Bluetooth beacons and whatever you like. That's a cool app. Okay? Yeah.
But is there an exhaustive library where non-mobile devices, how that can interact? And is there an exhaustive library that you have? Where I can refer, non-mobile, say, let's say there's an access mechanism, right?
So that I was describing at the beginning. If you are referring to IoT devices like Raspberry Pis, Intel Edison or whatever, those have adapters for the IBM MQTT message broker. So it's only a 3-liner of code. Even for Node-RED there are adapters, and you can basically read any type of sensor data from there. So for example, where's that Raspberry Pi here? This is an easy example. Using Node-RED or Python, you can read a lot of those sensors. Here's accelerometer, gyroscope, magnetometer, humidity, pressure, temperature, a button, yeah, all that sensors you can basically read out in one line of code or in a little Node-RED flow with 2 or 3 nodes. It's very straightforward. There are tons of tutorials. If you need one, just ping me. I will send you the best one for that. Okay, so now we have half an hour left, and I think that's more than enough time for our anomaly detector. Which is for today based on a library called Deep Learning for J. Okay? Deep Learning for J is powered by SkyMind. It's a Silicon Valley startup, and the brain behind it is called Adam Gibson. And it has a couple of components, and the most interesting one is ND4J. It's a Java VM version of NumPy for Python. It's basically a matrix or tensor library which supports those operations like vector-vector multiplication, matrix-vector multiplication, and matrix multiplications efficiently on a CPU double as efficient as NumPy. On a CPU enabled with the BLAST library, which is basically the vector units, using the vector units on your CPU even more, and on a GPU I think it's around 10 to 20 times of speed up. And in order to activate a GPU, you need only a CUDA installation on your server, and you have to swap one JVM system property to this one from ND4J native platform to ND4J CUDA version dash platform. And then out of the box, it uses the GPU. If you have more than one, I think you have to specify which ones you want to use. And if you want to run it on Apache Spark, all you have to do is to swap those 2 lines. So the first line is basically generating a neural network on your single machine, and the second is creating a neural network which can interact and run on Apache Spark. You can see that because one parameter is SC, which stands for Spark context. That's the way how it interacts with Apache Spark. Second parameter is the same like in the first call. It's the configuration of your neural network. We'll see this later, what this means. And the third one is the training master. So you see here training master, TM equals new parameter averaging training master. And parameter averaging is the so-called Jeff Dean style way of training a neural network in parallel on data partitions. That means you use the very same neural network, put it to multiple cluster members, and show the neural network only partitions, distinct partitions of your data, and then you train it on those data points for a number of iterations. And once you have done that, during the training process, training means you are updating the weights in your neural network. those are the weight matrices. Like in the linear regression model, you are learning A, B, C, D, like we have seen before. In the neural network, you are learning A, B, C, D, E, F, G, and so on. So a lot of parameters, and every couple of iterations, those parameters are sent to the training master from all the neural networks which have seen different fractions of the data, and all those parameters are just averaged. Just take the average of all and then send back, and that's all. That's the way how parallel neural network training works in the Google Brain, in deep learning for J, in nearly any library.
What's the difference between this and TensorFlow? Is it doing the same?
TensorFlow out of the box doesn't run on Spark, so it is capable of doing this parameter averaging, but then you have to install TensorFlow components. If you want to run TensorFlow on Apache Spark, all the Spark workers have to have a TensorFlow installation, and you have to use Tensor Spark for this. If you want to do only multiple training of different models with other parameters, you can use Tensor Frames.
When you use TensorFlow Spark, you are using DL4G.
No, if you are using Tensor Spark, you are using Apache Spark, TensorFlow, and some other components. I've not tested that. It's on my roadmap, but it's there. Yeah.
Apache Spark, does that come with the pre-trained packages? Like IBM Watson versus TensorFlow? Does this Spark comes as a pre-trained?
No, there's nothing pre-trained. Okay. Apache Spark has some out-of-the-box machine learning libraries. One is called MLlib, which runs on top of RDDs, and one is called Spark ML, which runs on top of data frames. But those are not pre-trained. You have to have data and train it yourself. TensorFlow, I've heard that there is a community which are having model zoos, like pre-trained models you can incorporate. But sooner or later, I assume there will emerge some interchange format like PMML for machine learning. Because actually it's relatively simple. It's the topology of the neural network which you have to represent somehow, and the weights. And it's very, very small, the size of a trained neural network, in order to serialize it to a file. And it's just a matter of time that the people are writing exporters, importers, converters, and so on. But at the moment it's not there. There are only a couple of frameworks which are kind of compatible in interchanging models, but there's no open standard at the moment. Yeah, so that's an example of a chat I had with Adam, and this guy is 24/7 online in Chitta. So if you have any questions about deep learning for J, either this guy or some of his colleagues.
Is there a chatbot?
No, it's not. He's just working, or maybe because he's San Francisco time, I'm Central Europe time. Whenever I'm hacking at the evening, late evening, it's normal work also for him. Anyway, he's always online, and that Alex Black and all those nerds, they are really good and helpful. So this is the demo. It's an Industry 4.0 use case where you basically attach such an accelerometer sensor to a bearing, and you measure the vibrations in each dimension. And since I don't want to take a broken bearing with me all the time, I've written a little test data generator. Actually, that's the old Python-based version. I have now a Node-RED version running. And that creates data based on a physical model called Lorentz attractor model. Have you heard about the Lorentz attractor model? Who hasn't?
Who hasn't?
Yeah. Okay. So Lorentz was proposing that model in 1963. He was one of the pioneers of chaos theory, and he found out that a very simple three-line model can generate chaotic data. And you see the chaoticness that this model basically oscillates between two semi-stable states. And when you change the parameters, the initial parameters only slightly, this picture will look completely differently. So that's basically how I generate my test data. I change the parameters slightly and I get a completely different view, but still it oscillates between those two semi-stable states. And that's a so-called phase plot. That means you can visualize 4 dimensions: the time, that's the line, and the 3 vibration dimensions in the healthy and in the faulty state. And in order to visualize that better, it's a time series or run chart where you see each individual component of the data set, and you see also 2 are highly correlated, and also you see that they are oscillating between 2 semi-stable states. You see it in the healthy one. In the broken one it's a bit harder to see. And now I can really easily explain FFT to you, because that's a time series. So this is like any vibration. It could be sound, okay? And sound contains different frequencies. So that's the time and that's the amplitude. And if you want to know which frequencies are present in your sound, in your audio signal, you can apply FFT, and that returns the spectrum. So these are low frequencies and those are high frequencies, and the amplitude of that particular frequency. That's FFT. I have a more mathematical explanation. Is anybody interested in that? FFT? Yeah? Okay, it's cool. It basically does the following. It takes the number of samples, and so basically the time, let's say 1 second, and then it generates sine waves, and with different frequencies from the lowest to the highest. So the lowest is the sine wave with 1 periodicity of 1 second.
Are you explaining FFT?
Yes.
Oh, no need.
Ah, you know. Okay.
I did a degree in communication engineering. So
Okay. Anybody else want to know how FFT works internally? Yeah.
Why are the oscillations just at the beginning and the end?
That's the frequency spectrum. You have only high and low frequencies present in the spectrum.
Okay.
That's the result of FFT.
I think one process that you haven't done, that's why it shows like this, is you have to apply FFT shift. So these two things kind of
A mirror.
like that.
No?
Yeah.
Oh,
Yeah.
then a second thing you have to explain me later. Yeah. Okay. So, okay. Are they mirrored? This as well? Oh my God. I was explaining that stuff at least 50 times, so I have to kind of inform all those.
Because it's very strange that you have nothing.
Yeah, that's true. That's really true. Okay.
And we're going out to the original time zone, which is odd as well.
Yeah, it's mirrored and
There should be a turn.
Okay. I still don't understand why, so I have to ask you later.
You use MATLAB to do this.
I used for this one I used R.
Oh, okay.
So I was a bit cheating because just let me finish the explanation how FFT works. It just creates sine waves in different frequencies, and then just calculates the correlation between the sine wave and your original signal for every frequency, and it does the same with cosine. And what I just did, I just removed all the cosine parts for simplicity. So you're not seeing any cosine frequencies here in these 2 spectra. But I don't know if that's maybe not the reason. What is FFT shift doing?
So I don't know. It's something that in MATLAB you usually come across a lot. If you just apply FFT, and this is like in the past, you would get something very similar to that.
Okay.
I came across as well. And then I had to apply FFT shift, which basically that part, that shift is so basically the beginning of the end is actually the beginning of the whole. So that little part that starts to vibrate again and go up, that's actually the the smallest frequency.
Okay.
It's just the way how to calculate it.
Okay.
So it's that function.
Okay. Let me check for FFT shift tonight.
This is nothing related to mathematics. So.
Okay. It still works, but I want to make it perfect, so I will.
Unless your signal is actually this, so you have lots of low frequencies and lots of.
Yeah, but
and
it's
nothing in the middle.
Yeah, actually, it's not mirrored. I have to say, it's
The reason
different.
why you have those on the right hand side is that if you go back.
Oh, it's mirrored here. You see here, there's a spike at the bottom left and a spike at the top right.
The reason why is because your sinusoid stops in an instant.
Okay.
You have to generate equal and opposing sinusoids to cancel it back down to 0. So that's the stuff on the right hand side. That's stopping all those sinusoids. So the left hand side is creating them. If that's how to think of it. Does that make sense?
No, but I'm tired.
Okay, go back to the previous page. Look
Okay.
in the time domain.
Okay.
So you have all these waves. They
Yeah.
start at 0
Yeah.
and they stop at 30.
Yeah.
So,
Okay.
So to do that in the FFT domain,
Yeah.
the spike on the left-hand side is setting all the waveforms up, and the one on the right-hand side is stopping all.
Okay.
That's how I understood it.
Okay.
Does that make sense?
Maybe. Yeah. So I have to do my homework with FFT. Yeah, I'm like proudly explaining FFT, and then I see I have to do more homework. No worries. But at least you see that there are more frequencies present and also more energy, even if it's mirrored. And so now I come to my autoencoder. An autoencoder is the last neural network topology I will explain today, which is basically a way of doing nonlinear dimension reduction. So dimension reduction, who knows what dimension reduction is doing? Okay, so there's an algorithm, for example, called principal component analysis, or TSNE, I think. And they are basically transforming your data, your high dimensional data with many columns, to a representation with less columns. And the idea behind that is it's not just removing columns, which it finds irrelevant. It transforms the data set, that it has less dimensions and still a reasonable amount of information in it. So it's a looseful compression. And PCA is a linear dimension reduction, and I will now introduce autoencoders, which are doing a nonlinear dimension reduction, which is better. What you do is, to get an autoencoder up and running, you have a feed-forward neural network or any type of neural network, but the key thing is you have a so-called bottleneck in the middle, and that's the number of neurons you have here are the number of reduced dimensions. And what you do is you show the input, you show the neural network data at the input and at the output, the very same data at the input at the output. So that's unusual. Normally, you show a neural network your training data on the left-hand side and your target data on the right-hand side, and then it tries to predict the target out of the input best. Okay? But if you show the neural network the input, the same input at the output, it tries to reconstruct, or it learns to reconstruct the given output based on the input. And so it tries to reconstruct the input on the right-hand side. But if you have a bottleneck here, it still can do it, but it has a harder time, and that means it will not learn any noisy and irrelevant data, and that's all about what dimension reduction is. But it's nonlinear because you have nonlinear activation functions in your neurons, therefore you have a nonlinear overall model here, and therefore you have a nonlinear dimension reduction. And we are actually using this now in order to create an anomaly detector, because if we train this neural network with healthy data and it learns how to reconstruct healthy data, then it will have a harder time if it has to reconstruct faulty data which it hasn't seen before. Is that, yeah?
I have a basic fundamental question with autoencoder.
Yeah.
In fact, two questions. One, here people using autoencoder for traceability, like you feed back the outputs as input,
Yeah.
and see what the neurons, how it is connecting, the weightage, all those things. Is that true?
No, you don't care.
Okay, you can't use it for traceability. I mean, how it's predicting, how it's behaving.
Oh, I think you never can do that in a neural network. If it.
Yeah, because people do that. People say that, at least they do that. And because of non-linear, I was skeptical. How can they do it?
No, actually, what you can do is you can read out whatever happens at the compressed vector. And maybe most of you know the MNIST data set, the handwritten digit classification data. You can run this through autoencoder. There's a R implementation with the H2O framework. You can Google for that, Ecosia for that. And excuse me?
Which one?
The framework is called H2O, and the programming language they are using is R, and it's the MNIST data set. If you search for those three terms, you will find it. Excuse me? handwritten digit recognition. Yeah. And they are basically running through a two-dimensional autoencoder, and then they plot those 2 dimensions. I have it on my laptop. Maybe I can just show you later, if you are interested. Anyway, so they are reading out the 2 dimensions and they're plotting it, and then you see a relatively good separation of all the numbers based on that compressed representation. You see overlaps, for example, 9 and 8, they are quite overlapping, but 1 and 7 are overlapping, but I think 8 and 1 are relatively distinct. Okay. And in theory, if you want to do, you can compare it using PCA and compare the autoencoder and PCA and see how the nonlinearity improves your separation of the data. Anyway, that's the idea, and the additional idea is I have LSTM neurons up front, so they are recognizing temporal patterns, and that whole package I'm implementing in deep learning for J.
Where are the LSTMs?
Excuse me?
Where are the LSTMs?
In this picture they are nowhere,
Okay.
but you will see it later in the Java code.
And what's the benefit of deep learning for J over TensorFlow and the other platforms that are out?
Okay, so the advantage is that it is a first-class citizen on Apache Spark. It's implemented in Java, and it runs on every Spark cluster because you can build this application, which you are seeing here, and export it as a single self-contained jar file, and you can just run Spark submit and the jar file, and it runs. In TensorFlow or in TensorSpark, you have to install TensorFlow on each worker, which is in some platforms not feasible. And the other thing I'm currently trying out is a library called Apache SystemML, which is a very hot thing because SystemML has an optimizer for matrix algebra. It takes the sizes of the matrices into account and generates different execution plans. And it runs on a Raspberry Pi on a Java VM anywhere. So it's even a bit more promising, but let's see. I'm trying out all those 3, and I definitely will talk about those in future. So let's run this. That's a little application which uses the IBM Watson IoT jar files or API in order to connect to the platform. So first what happens is the deep learning for J backend gets initialized. You see here 4 threads, and it uses 10 GB of memory, 8 cores. It uses already OpenBlast, so it uses the vector units. So the ND4J library in it will use the vector units for all that vector matrix computations which are taking place. And then the red stuff is the client connecting to the IBM Watson IoT platform, which still is MQTT, and now it's waiting for data. Okay, so excuse me.
Is it using GPUs?
No. During the AI Summit, I found out that it's not possible to use it on my machine because it expects CUDA to be installed, and I was always failing to install CUDA on my machine. And now some guy in the audience told me it's because I have an AMD GPU in my MacBook and not the NVIDIA one. So on the cloud you can use it. In the IBM Cloud you get NVIDIA P100 card, which is the fastest at the moment at the rate of $1 per hour. So,
But there's another package, instead of CUDA for NVIDIA, right?
Yeah.
There's another package for AMD that they've...
okay, but I don't know whether ND4J is compatible with that other package, so I have to check that. We can chat with Adam Gibson later during our beer session and ask him. But yeah, so that's my Lorentz attractor. I won't go into too much details because I only have 4 minutes left officially. So those are the 3 model updates. So you have H, A, B, C. Those are the initial parameters of the model. And then you have X, Y, Z. Those are containing the model state. And on every time step, you are updating X, Y, Z based on the historic values of X, Y, Z, plus taking that model parameters H, A, B, and C into account. And then I'm just storing the state back and generating those tuples in this model at the rate of 100 Hertz or 100 messages per second. And I'm limiting it to 3000, that means 30 seconds worth of data, because I told you if you're doing online learning, your compute power has to be in line with the data rate. And since this is not the case on my MacBook on a CPU, I have to stop after 30 seconds. Then I send the data using that connector to the MQTT message broker. And just for debug purposes, I have those two nodes, but they are not necessary. And then here I can switch states. So you see here. Excuse me? What is that?
The hidden node on the neural network.
That's the test data generator.
Oh.
Yeah, so the neural network comes later. So I'm now switching to healthy. That means I'm just setting those 4 model parameters. And if I want to set it to broken, I'm just changing those 4 model parameters. Okay. Let's do that. So I click on reset. So I'm resetting basically that wall to 0. Then it will let pass 30 or 3000. I have to, whatever, 30 seconds worth of data are being sent to the MQTT message broker. And now a so-called window is filling up. There are, in stream processing, you always are working on windows, and there are 2 dimensions on those. They are either tumbling or sliding, and either time or count based. At least I only heard about those 4. Tumbling means it's like filling up, and whenever it is full, it's doing the computation on it and then uses the next one and waits until the next one fills up. Sliding is like acting like a FIFO queue. And then count-based is obvious. It will wait until it has 30,000 or 3,000 messages. And time-based, you need a timestamp in your data, and then you can say this window is containing that data from a certain period of time. So you see here that I'm running iterations. So that's a usual thing to do. You are always training a neural network in iterations, or so-called epochs. And that means you are showing the neural network the same data multiple times, in contrast to just only once. And in order to train better, you decrease the learning rate and you show the data multiple times to the neural network, and that gives you a better performance. And the very, very right-hand side number here is the reconstruction error. So it now learns how this data looks like.
And what's the rate of convergence?
Excuse me? It's converging, yeah.
Yeah, but what's the rate? What's your expected value? What do you try to
it's not normalized. So the more neurons you have, the higher that value gets. So you would have to normalize it. I'm already happy that it converges, and I'm happy that it's not oscillating. So that depends on the hyperparameterization of your neural network, and that's black magic. So there's no good guide explaining that.
Is there an estimator to look at that optimum parameters?
No, the only thing what I am aware of is Monte Carlo simulation and grid search, which basically means you just try out in that hyperparameter space all possible combinations or a subset of all possible combinations and rerun it. That's how people are doing it currently. If you come up with a better solution, you will get rich at the moment. Maybe in 2 years it's too late, but So after 1,000 iterations, we will end up at a certain value. And let's run this another time after this is finishing. So see, it's kind of converging to 180.
180 what?
180 Romeos. No. 180 is the root of the sum of the squared errors of all the neurons. Like I said, it's not normalized. The more neurons you have, the higher the value is. So you kind of can normalize it based on the number of neurons and whatever you think is feasible.
So why are you using LSTM? Why not just feed forward?
Because I want to take the time domain into account. It's a time series. It's oscillation. It's time series data. Therefore, I'm using LSTMs.
What's the code like with the LSTM? So it's simple.
Yeah, I promised to show you. Let this work in the background. And let me find I have multiple versions of it, so let me find the correct one. So let's start from run. I have to find the correct implementation. So run is nothing else than it's IoT anomaly example LSTM FF. Oh, I'm using FFT still. Okay, good to know. So it's using LSTM and FFT, and let me just search for this. Oh, the horns of your emergency cars have the same sound like in US, no? Yeah, in Switzerland, in Germany, it's da 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 da, you know? So I wanted to show you the code, sorry. So that's some FFT I'm doing. I'm using some FFT library. It's actually not so easy to find a FFT library for the JVM. You find hundreds or thousands for R, and you find one working one for Python. Yeah, and I found one for Java, so I'm using that one. So that's the neural network configuration. There are some global parameters, like for example, Adagrad. You can Google for that. The global activation functions it should use, then the optimization algorithm, which is stochastic gradient descent, learning rate, regularization for prevention of overfitting, and so on. And then you have here the first layer, and that's the LSTM. So this is these two lines of code, or that one line of code is generating an LSTM layer. What you have to provide is the number of input and output neurons, and the next one is autoencoder. So what you can do, you can use a simple normal layer and just compress it by the number of neurons, and you can also use the out-of-the-box autoencoder, and that's a variational autoencoder, which is a further development of an autoencoder, which you can use, and it has some parameters, and then you have an output layer. So I have to come to the end because it's already past 9, but it will be finished in another minute. Yeah, and then you have this multi-layer network configuration, and then you basically have here detect. So you see here 300, and now I switch to broken and do it again. Let's see what happens then. And in parallel, I'll explain you the code. So I'm calling fit, and I'm calling fit, as you can see on the left and on the right hand side of the neural network. I'm showing it the same data. That's the way how to train. And then I just call one score. So fit controls the neural network and tells the neural network, please update yourself and learn something, and score tells it to not learn something. But I'm always calling fit. Even now I'm sending faulty data to the neural network, and then it will learn on the faulty data, and it will also have a decreasing error, but the end result of that time window should be far higher than 300. And once that is finished, we can. Yeah?
Any tool is provided for monitoring heart weight, beers, and the loss.
Excuse me?
Any tool is provided for monitoring.
There are different listeners. You see here it's a score iteration listener. And there is also a histogram listener which in the background opens a web port you can connect to, and you get some graphs. And then you see if it oscillates, or you write it in a CSV file and analyze it in R.
Yeah.
Can I make the announcement of the startup or wait until the finish?
Maybe just wait to get the best feeling out of it. And then, you see it's still 40,000, but it decreases fast. Yeah, only 700 iterations to wait, and then.
So why do you have the LTSM in the first layer?
Because I want to recognize the time series, the temporal properties.
That you want like a feature layer for the memory?
Yeah, I want to recognize the distant, temporarily distant events, and therefore I need to have memory in the neural network.
Yeah.
And therefore I have a LSTM layer.
But why do you do that on the first layer?
I don't know. I just put it there and it works.
You want some features first and then
Yeah.
TM higher level.
I have to think about that. Good question.
I guess my argument is that the LTSM can only learn to remember a linear function of the particle position.
No, the LSTM should be able to learn anything because it also has nonlinear functions in it. So LSTM is just an extension of a neural neurons with a memory cell and 3 additional signals: input, forget, and output.
But it's because it's in the first layer, it's input is only the particle position.
Excuse me?
Because it's in the first layer.
That doesn't really matter where you put it, that layer. You can even have multiple LSTM layers in your neural network. So only 200 iterations to go, but most likely we will end up with something bigger than 300, and then it's basically proven to work. So 100 to go. Yeah, it's still 18,000, you see. Yeah, it pretty works. You get always different values because there's a random number generator for initializing all the weights, but it's behaving always like this. You see, it's far above 300, okay? So,
Hi, I want to tell you about our new startup. Optilum is a new startup based in Oxford, and our vision is to enable better early diagnosis and treatment of cancer by using machine learning to unlock new insights from large imaging archives and the electronic medical records, and by making that available as an expert-level decision support system which helps to turn every doctor in the world to help them achieve the same performance as the best experts. Why join? We're actively looking for new colleagues. Why our company? You see a lot of startups who start with machine learning, looking for applications, and our key difference is that we actually start from the problem and a sequence of important clinical problems, and we work with the top doctors in the authors of guidelines in UK, US, Germany, and Netherlands to actually help guide our development that we solve a real problem. Second, because we work with these top doctors, we also have a unique access to big data from 12 large hospital trusts in the UK, Germany, and Netherlands. And also, certainly because of the people, we were all members of the Oxford Computer Vision Lab at some point in our careers, which is considered the best in Europe. and actually Mike, our chairman, founded that lab, and we keep working closely with end users at Oxford and DeepMind to help us stay up to speed. And most importantly, my colleagues have more gray hair than me, and they actually founded a number of successful companies in medical imaging, including successful exits and an IPO. And last but not least, we also are now signing our investments tomorrow. So we raise a lot of money from patient investors. That's important in healthcare. From Sir Martin and Audrey Wood, the founders of Oxford Instruments. That was the first spin-off out of Oxford, now a big corporation with 2,000 people. They also funded, they were the only seed investors in Sophos. Again, now a big company with 3,000 people, and Natural Motion Games. And the St. John's College, the Wealthies College in Oxford, and then a number of medical doctors, the professors of medicine, and entrepreneurs in computer vision and medical imaging who will help us build a company. So we look for colleagues who want to make a real impact on an important disease such as cancer, and we look especially for research scientists in computer vision and machine learning, and for software engineers a little bit later, but we are actually ready to hire software engineers already now. So feel free to talk to me with a beer afterwards. Thank you.
Okay, thanks a lot. I hope you enjoyed, and if you can stay a bit, have a beer with us. Otherwise, have a safe journey home. Thank you.